Hello everyone. My name is Magdalena, and today I'm gonna tell you about measuring metallicity in outflows. Specifically, I will be talking about this galaxy that you can see here, NGC 1569. So a quick overview on how do metals get into the outflow. So metals are created in the galactic disk through the formation of stars, and eventually these stars explode into supernova explosions and eject really hot metal-rich gas outside of the disk. But this is not the only gas that we can find in outflows, because due to the energy of the explosion, there is also ISM entrained gas that gets in the outflows. So actually we can find a mixture of this really hot gas and this ISM entrained gas in the outflow. And this is a way in which metals get redistributed in and around the galaxy. So this process is, as you heard from Ron, really important for many aspects of galaxy evolution and some properties of the ISM and star formation. For example, we have here the classic mass-metallicity relationship. And you can see in the background observations that we observe a good relationship. However, for a single mass, we can see that there is a dispersion of different metallicities. And this can be explained by the outflows removing more or less metals from the disk. So the more metals are being removed by the outflow, we will measure a lower metallicity. So this process, we want to constrain this process, and there are some models like the ones that are over plotted in here that explain this mass metallicity evolution. But this is really hard to constrain observationally, because measuring metallicity in outflows is not easy. We cannot use the classical strong line method because the environment in the outflows is really different from the environment in H2 regions. So ideally, we would like to use something like the direct method. This method uses auroral emission lines like O3-4363 to get electron temperature, and from that we can measure metallicity. The problem is that these emission lines are really faint, so they are really hard to observe, and we really need deep observations or large telescopes to observe them. So this is the work of Cameron et al. 2021, and Diane talked a little bit about this, but in summary, they were able to observe O3-4363 around this galaxy. So here we can see an HST image of the galaxy. We can see it's an edge-on galaxy. And the pink contour shows all the regions that they observe O3-4363, so they can measure metallicity in those regions. So essentially, we have a metallicity map all around the disk and in the disk. So in this plot, along this axis is the galaxy, and we can observe that in the edge of the major axis, we observe the lowest metallicity, and in the edge of the minor axis, we observe the highest metallicity. And yeah, this is consistent with the picture of metal poor inflows and metal-rich outflows, and this is the first time that this was observed for a single galaxy with a consistent method. So how can we translate this to something that we can input into models like the ones that I show you for the mass-metallicity relationship? So there is this parameter, pi y, which essentially tells me how many metals are retained by a galaxy. So the higher pi y, the more metals are retained by the disk, and the lower, the less metal. Or another way of thinking about it is the lower pi y, the more metals are being removed by the outflow. So these two curves show different models, and this pink point here shows the observations and the value that we got from the observations of Cameron et al. And as you can see here, the observations suggest that we have more metals being retained in the disk than what we expect from these analytical models. So one concern that we have with these observations is that maybe there is a bias due to the low resolution. So one way to address this is to observe a close-by galaxy like NGC 1569, which is a really close-by galaxy. It's so close by that it's blue-shifted. So we can really resolve the individual filaments of the outflows. So in this image, you see in red H alpha emission, and you can see how it extends beyond the disk. So we observed this with 3 different KCWI pointings, 2 along the disk and 1 over this filament that you can see here. And we detected all 3, 43, 63 in almost all the field. And you can even see the filament structure in all 3. So yeah, from this emission line, we can get the metallicity using some models. And here I'm showing you 4 different maps in this part of our observation. So at the top you have the disk, and at the bottom you have the outflow. And here in the continuum, you can see like we have a lot of continuum on the disk. This is a star, and this really bright point is a superstar cluster that we can also observe in HST. And here we have H beta map. And again, you can clearly observe here the outflow filament that's also observable in H alpha. And it's also interesting to look at this in the ionization map, because we can still differentiate this structure of this filament, outflow filament. However, when we go to the metallicity map, this structure seems to disappear. So it doesn't seem to be a big metallicity difference between the outflow filament and what's outside of the filament. So to really test this theory, and because this will help us to understand how the resolution could affect the other observations we have from Cameron et al. 2021. So essentially, the difference in resolution is in this sample. My sample is 20 parsec resolution each pixel, and the measurement before is 500 parsec resolution. So each, like, all this area of my observations equates to roughly 1 spaxel of the previous measurement. So to see that the lower resolution, so to understand whether the lower resolution measurements were biased for the more bright parts of the outflow, I separate this sample into 2 different samples, the brighter in H beta and the faintest in H beta. And here I have a plot of the distribution of metallicity corresponding to the 2 samples. And you can see that they have roughly the same metallicity, even though there is like a small tail here of low metallicity for the fainter spaxels. This could be due to the entrained gas versus the outflowing gas. So that's also an interesting result of this. But essentially, since both samples have the same mean value, we shouldn't expect the lower resolution to be biased towards these really bright filaments. And here I'm showing you a profile, a metallicity profile of my galaxy. So x-axis is distance along the minor axis, with 0 is the midplane of the disk. So the kind of pink area here is what corresponds to the disk, and the white area, it's the wind or the outflow. And this peak here corresponds to the part where we observe the superstar cluster that has a little bit of a higher metallicity. So I calculated the average metallicity using both pointings that we have on the disk. And it gives this value. And for the outflow, we have this value here, which are roughly the same. The difference is within the error bars. So it's a flat metallicity profile, essentially. And how does this translate to our pi y value, where we want to compare with the analytical models and our previous observation of mercurium 1486. And as we can see here, a reminder, pi y represents the amount of metals that stay in the disk. So again, we are observing that galaxies retain more metals than what we expect from the models. And yeah, we would like to add more observations to this plot. And from this work, one other conclusion is that the resolution did not significantly impact the metallicity measurements in outflows. So that's great news because we can add some other targets that are farther away. Thank you.